Okay, good afternoon, everybody. So we're talking about interfaces in class in the previous lecture. So in the previous lecture, we implemented two different interfaces, and in doing so, we actually used an inner class. So today, I'm going to show you how to create your own interface and explain why you might want to do so. And then we're going to move on and look at another example of interfaces using a data structure. All right, so the reason you want to make an interface is because you have one or more classes, usually more than one class, that you want to treat in the same way. So in other words, they all implement a given interface, but they also have, but they're different from one another. So for example, you have array list and you've got linked list. They both implement the list interface. So you can treat them as though they were just a list, right? So you can get, set, add, remove. Right? And you know what operations that you can perform with either an array list or a linked list. However, the performance of array list and a linked list are very different. So without going into too much detail, an array list is usually more efficient than a linked list, except in very specific cases. And we'll look at array lists and linked lists in more detail later on. Another example are the sets and the maps. Right? So you have a tree set and you have a hash set. You've got tree map and hash map. Right? So both tree set and hash set are types of sets. So you can treat them as though they were just sets. So you can add, you can get, you can ask if it contains a value, et cetera, et cetera, et cetera. Right? So in other words, you can just use the set interface to use the sets. However, tree sets and hash sets behave very differently. Tree sets keep their elements in a sorted order. Hash sets are generally faster than tree sets for most operations. Right? So you want to create an interface when you have a reason for creating multiple classes that you want to treat the same way, but they behave differently, right? Or they have different properties. So to create an interface, it's very easy. You just create something that looks like a class. Right? So instead of creating a class, you create an interface. And then you have to remember everything in an interface is public. Right? So even if you don't declare the access modifier, Java considers everything in the interface to be public. Right? So we can make a not very useful interface called printable. Right? So printable is just an interface for objects that can print something, that can print their contents to standard output. Right? So this isn't very useful because you already have a print. You already have every object has a toString method, so it's easy enough to print something. But we'll make an interface just for the purposes of an example. Right? So you make your interface. It's public. Right? Use the keyword interface. Give a name to the interface. Right? And now, to the body of the interface, you just put in the methods that you want every object that implements the interface to have. Right? And you end each method with a semicolon. Right? So our printable interface has only one method. It's called print. Right? Again, everything's public, and this print method happens to return no value. Right? So this print method just prints the object to standard output. Right? And so there's our interface. Right? And now you can take any class that you have access to its source code, and you can make it implement the interface. Right? So for example, I can take the point2 class, and I can now say point2 implements the printable interface. Right? And so point2 we've already modified it once to implement comparable. So a class can implement as many interfaces as you want. Right? So we can also implement the printable interface. Right? You just separate the interfaces with commas. Right? And a lot of the classes in the standard library implement many interfaces. Right? So because we're now implementing the printable interface, we have to add our print method to the class. Right? And to print a point, it's easy. You just call toString on the point and print out the point. Right? And so it's in this case, it's very easy to modify our class to implement the printable interface. Right? And now, if you have someone can make a list of printable objects, right? Because an interface is just a type. Right? So the printable name defines a type. Right? So now someone can make a list of printable objects, right? And they can add any object to that list that implements the interface. Right? So they can add a bunch of points and then print the points just by looping over the list and then calling the print method on each object in the list. And so there's an example of creating a very, very simple interface. Right? All right, so any questions so far about interfaces? Okay, so I now want to, so the use of interfaces really becomes really apparent when you start to implement different data structures. So if you stay in computing science, eventually you'll run into the data structures course, and you'll learn about a bunch of different data structures, right? And you'll also learn how to implement the same data structure in multiple different ways, right? So for example, you'll learn how to make a list using an array and using a linked sequence of nodes. And we're actually going to do that later in this course, right? But you've got two different implementations of a list, which you might want to offer to people to use. And you want to let them use it in the same way. So what you do is you make a list interface, and you have both of your classes implement the interface. So as a first example of that, we're going to talk about this data structure called a stack. Right? And so a stack is a type of data structure that sort of resembles a physical stack of objects. Right? Here we've got a stack of files, we've got a stack of books, we've got a stack of pancakes here. Right? Every stack, the data structure type stack, has this notion of the top element of the stack. Right? So here we've got the top book of this stack. Right? And in a classic stack, the only thing that you can do with the stack involves the top of the stack. So you can only do two things with the stack. You can push an element on top of the stack, right? So that just puts another element onto the top, right? And then you can pop an element off the top of the stack, and that just removes the element that's on top, right? If you pop an empty stack, that typically results in an error of some kind, right? So in Java, you throw an exception, right? And that's all that you can do with a stack. And you might think, well, this seems pretty useless, but in fact, it turns out to be incredibly useful, right? So a lot of algorithms that you would implement rely on having a stack available. Right, so push to illustrate. So we start out with an empty stack. Right? If I push an element onto an empty stack, so this is a stack of strings, right? You end up with a stack that has one element, right? And the top of that stack is that element that we just pushed onto the stack. Right? So if I push another element onto the stack, right? We now have two elements in the stack, and the B is now the top of the stack. Right? And so on, and so on, and so on. Right? So now we have a stack of 5 elements. Now remember, the only thing that you can do with a stack involves the element at the top of the stack. So if I want to start taking elements out of the stack, right, they start to come out from the top. Right? So for example, if I pop the element, the stack, right, then the E comes off the stack and gets returned back to the caller. Right? So S in this case is the string E. Right? So the element disappears, and then the top of the stack moves down to the next element in the stack. Right? And so the current top of the stack is now a D. If you push more elements onto the stack, right, then they end up going on top of the D. Right? So if we pop the stack again, the D comes off. Right? Top of stack moves down one. Pop again, the C comes off. Pop again, the B comes off. And if you pop the last element, you end up with an empty stack again. Right? And so notice that the first element that went into the stack, the A, that's the last element that comes out of the stack. Right? Do I tell you where? Oh, no. So stacks are what are called first in FIFO. FILO. First in, last out. FILO. So it's an FILO data structure. Right? The first element in is the last element out. So and as I mentioned before, you can only do these two operations with a stack, and you might think that this isn't very useful. Right? But it turns out to have many, many uses in computer science. Right? So if you ever use undo or redo in your some sort of program with a graphical user interface, right? Like Word or PowerPoint or something like that, right? Undo and redo are implemented using a pair of stacks. Right? So every time you do something in your program, right, in PowerPoint or Word, right, that gets interpreted into a command. Into something that resembles a command object, right? So typing in some text, that text gets wrapped up in a command object, and that object gets pushed onto a stack. It gets pushed onto the undo stack, right? And then you use some more stuff, and then another object gets pushed onto the undo stack. And you do some more stuff, and another object gets pushed onto the undo stack. When you press undo, that command that's sitting on top of the stack gets undone, right? And then that gets pushed onto the redo stack. Right? If you now redo what you just undid, the element on the redo stack gets popped off, and whatever is stored in there gets redone. So it's, stacks are widely used in this problem called parsing. So parsing is the problem when you have I guess the easiest way to describe this is parsing is when you have a program that needs to read and interpret text of some kind, right? So your Java compiler has to parse your Java source code, right? In other words, it has to read your source code and then determine, is this a valid Java program, right? A lot of parsing algorithms rely on stacks to work properly. Whenever you call a method in a Java or C program, actually most programming languages, what ends up happening is that method, information about that method gets pushed onto what's called a call stack. So the call stack stores information about the active methods in a Java program. Right? So if I call my main method in a Java program, something that resembles a main method gets pushed onto a call stack. If the main method calls another method, that method gets pushed onto the call stack. If that method calls another method, it pushes that other method onto the call stack. When a method returns, the method comes off the call stack. So all the information, well, yeah, I guess all the information that the runtime needs to know about a method, this all gets stored on what's called the call stack. Right? And then finally, if you ever have a recursive method and you have to convert it into a non-recursive method, so convert it into the iterative version of the method, then the way to do that is to use a stack. Okay, so an example of using a stack, I'm just going to reverse a sequence. Right? So I'm going to use the fact that the last element you push onto the stack is the first element that you push onto the stack is the last one to come out. So I'm going to use that fact to reverse a sequence. Right? You shouldn't do it this way. There's much more efficient ways to do this. Right? So I'm going to reverse a list of strings t, and I'm going to return the reversed list. Right? So I want to reverse the list t, and I don't want to modify t. I don't want to permanently modify t. Right? I want to give back the caller a version of the list with the elements in the reverse order. Right? So the first thing we do is we make a new list, and I make a stack. Right? And then I'm going to take all the elements in the list. Right? So I'm going to iterate over the list and push each string in the list onto the stack. Right? So what happens is the first element in the list, that's at the bottom of the stack. The last element in the list is at the top of the stack. Right? So now, while the stack isn't empty, I just pop the stack. Right? So the last element comes out, and I add that to the result. Right? Then the second last element comes from the original list comes out, and that gets added to the result, and so on and so forth. Right? So if we start out with the list A, B, C, right? Here's my stack. It's currently empty. Here's the resulting list, which is also currently empty. Right? I'm just going to push the elements of the list onto a stack. Right? So A, then B, then C. Right? Now I'm going to pop the stack and put them into the result as they pop off. Right? So the C comes out and goes into the result. The B comes out, and then the A comes out, and you end up with a reversed sequence. Right? Of course, you shouldn't do it this way because you don't actually need the stack structure here. Right? You can just loop over the list backwards and put the elements from the original list into the result list. Right? But this example illustrates the first in, last out property of a stack. Okay, so this little picture here of this stack, if you sort of stare at it and you turn it sideways to the right, then that just looks like the original list. So in other words, a stack kind of resembles a list. Right? So when I push an element onto the top of the stack, that's just like adding an element to the end of the list. Right? And when I pop an element from the top of the stack, well, the top of the stack's at the end of the list, right? So that's just like removing an element from the end of the list. Right? And so it looks like you can implement this class, a stack, using an array list. Right? And you can, and it's like 10 lines of code. Right? So we can make a stack class. This is going to be a stack of strings. Right? Internally, there's just an array list of strings. Right? Our constructor makes an empty stack. So what do you do? Well, you just make an empty list of strings. Right? So the stack is a new array list. Right? It's useful to know how many elements are in a stack. So it's useful to implement a size method for your stack. So how many elements are in the stack? Well, it's just the number of elements in the list. Right? How do I push a string onto the stack? Well, I just add an element to the end of the list, right? So let's just add. How do I pop an element from the end from a stack? Well, I just remove the last element, right? So I can just remove the element at size -1, right? So for an array list, when you remove an element at the end of the list, that occurs in constant time, right? So that's O1. When you push an element onto an array, when you add an element to the end of an array list, it's usually O1. But every once in a while, it's ON. And I'll explain. So the reason it becomes ON is because if you have an array list and internally it has an array of, say, 5 elements, right? Then when you add the 6th element to the list, it has to make a new array, right? Because it needs space to add the 6th element. So it has to make a new array, copy all of the existing elements into the new array, and then it adds the element to the new array, right? So that making a new array, copying the elements from the old array into the new array, that's ON, right? So every once in a while, that push operation requires ON time, but most of the time it's O1. Okay, so that's implementing an array, a stack using a list, right? So using a different data structure to actually implement the stack data structure, right? And the implementation here is actually, our stack is a composition of a list, right? It's a composition because it never makes that list object available outside the class, right? So internally it makes a list object, right? And then none of the methods here return a reference or involve changing this reference here, right? So this is just a composite. So here we've got a stack, which is a composition of a list. Right? But there's at least 2 other ways of implementing the stack, right? So number 1, instead of using an array list, we can use a plain old array to store the elements, right? You might wonder why you want to do that, and the answer is it's because it's good for you, right? It's educational. Right? In Java, you wouldn't bother because they've already got a standard library that does all this stuff for you, right? But at some point, you need to understand how to actually manage this array yourself. So now is going to be the time, right? So instead of using a list, we can use an array, right? The second way you can do this is to use what's called a linked structure. And you haven't seen this yet, I don't think, in any of your courses. And so we'll look at doing this as well. Right? And you might ask, why would we bother doing it these 2 different ways? This way seems to work just fine, right? And so the answer is both of these alternative implementations have their own advantages and disadvantages, right? So you're going to see that creating this linked structure, right? So here, push is usually O1, but sometimes it's ON. If you use a linked structure, you can guarantee O1 time for both of these operations. Right? So you can actually guarantee better worst-case complexity using a linked structure. Right? All right, so if I have 3 different ways of implementing a stack, and I want my users to be able to use all 3 different versions depending on which one is best for them, then the way to do this is make an interface, right, that has all the common operations that stacks should have, right? Implement the different versions, right? And then let the users pick which version is most appropriate for their purposes, right? And they can use all 3 versions in the exact same way, right? They just use the methods that are defined in the stack interface, right? If later on they decide, oh, hey, I should have used this other stack, right? Then it's trivial to change their implementation to use the other stack, right? When they make their stack object, they just make a different type of stack, right? And then the rest of their code all stays the same. Oh, okay. So let's see how to implement a stack. Okay, I'm going to skip over the first set of slides. I may come back to them if there's time at the end of the lecture. So the first set of slides show you how to take a recursive method and turn it into an iterative one using a stack. But I'm going to skip over that first and come back to that. Okay, so what I want to talk about is how to make a stack using an array instead of an array list. And it turns out it's pretty similar, right? So instead of using an array list, I'm going to use an array, right? But what you have to remember is that arrays in Java and many other programming languages, they can only hold a fixed number of elements, right? So if your array ends up being full and you want to add another element to the array, then what you have to do is you have to make a new array, right? That's bigger than the original array. Okay. So to implement this class, right, using an array, you need to, so implementing the stack using a list, you just add and remove from the end of the list, right? But in an array, there really isn't a built-in end of the array, right? So what you need to do is you need to keep track of how many elements are in the stack, right? And that tells you where in the array you're going to be adding and removing elements from, right? So I need a field that keeps track of how many elements are in the array, right? So we're going to make a stack of int instead of a stack of string, right? So internally, we're going to have an array that's just an array of int, right? And then I'm going to keep track of where is the top element in the stack, right? And so that field that keeps track of where is the top element is called top index. Right? If the stack is empty, then top index is -1. Right? Do I have a picture here? Okay, so here's a picture of an empty stack. Right? Default capacity, that's just the starting capacity of this array. Right? So I've got an array of size 16. Right? Now in Java, when you make an array of anything, an array of primitive type, it all gets filled with zeros. Right? So if you, for an array of int, you end up with an array of 16 zeros. My top index is -1, right? So remember, -1 indicates that the stack is empty, right? And so our empty stack looks like that. Right? And how do you implement that constructor? Well, it's easy. You just make a new array, right? So remember here, I've got a field called ARR, but it's not actually an array yet, right? It can store an array. There's no array object for that thing yet, right? So the constructor has to make an array object. Right? And then it has to set the top index to -1. Okay, when you push a value onto the stack, so suppose I want to push a 7 onto the stack, right? Then I want to write a 7 into the first free space in the array, right? So the first free space is the element at index 0, right? Which is just 1 bigger than the top index, right? So to push a value onto the stack, you just add 1 to top index to indicate that, hey, the top of the stack is going to move up by 1, right? And then set the element in the array at the new top index, right? So in other words, when I push a 7 onto this stack, I'm going to make this go up by 1. So that's now index 0, which is here, right? Then I'm going to set that element to the element that we pushed onto the stack. So we're going to change that element to 7, right? So our picture is going to look like this. So push the 7, top index goes up from -1 to 0, set the element at index 0 to 7, right? And this is easy. Push a -5, so I'm going to make, right? So when we push -5, we're going to increase that index by 1, so it's going to go up to 1. Then I'm going to set the element at index 1 to the -5. Do I do it again? Okay. How do you pop an element off the top of the stack? Well, top of the stack is pointing at the, I guess, the light blue element there, right? So to pop the element, we get that element at the top index, right? And then we, whoa, sorry. Right? So get that element that's at the current top index, decrease the top index by 1 because the top of the stack comes down by 1, and then return the value, right? You don't have to overwrite the value that's stored in the array, right? So we've got a 7 and a -5, right? When I pop the stack, I'm going to remember what that value is, right? So value equals -5, right? Decrease the top index by 1, so top index goes down to 0, right? And then return the value. So I'm going to return the -5. Right? Okay, so how do you pop a stack? So ignore the if statement first, right? Get the element at the current top index, right? Adjust the top down by 1, and then return the element that we remembered 2 steps ago. Now, you can't pop an empty stack, right? So how do you know if the stack is empty? Well, the top index is -1, right? And now you can see why you can't pop an empty stack, right? Because here, if I try to get the index at -1, the element at index -1, right, that's an illegal index, right? That throws an exception. So if the top index is -1, if the stack is empty, right, throw some kind of exception. Okay, any questions so far? Yeah.
For the stack class, why do we set the default capacity to like final?
Here?
Yeah.
Why is it set to final? So I mean, it's supposed to be a constant, right? So this is the starting capacity for any stack, right? So it's supposed to be constant, right? You don't want this really, and I'm not going to change it anyway, right? So nowhere in the class am I ever going to change the default capacity, right? So in this case, it makes sense to make it final so that I don't inadvertently change it. Where did push go? Oh, we haven't implemented push yet. That's right. Okay, so with push, you have to worry about running out of space in the array, right? So this is a stack where I can safely do one more push, right? So the top index is currently 14, right? And there's room for one more element, right? So that's fine, right? So if the top index, so what's the 14, right? The 14 is equal to, the 14 is less than the size -1, right? The size of that array is 16. 16 minus 1 is 15, right? So as long as that index is less than the size of the array -1, I can safely push an element onto the stack, right? So if the current top index is less than the array length of -1, right, go ahead and increment the top index, right? Then go ahead and set the array at top index to the pushed element. Right? Okay, now what happens if there isn't space? Right? So if you run out of capacity in the current array, the only thing that you can do is make a new array. Right? So that's your only option here. Right? So what you have to do is you have to make an array. The array has to be bigger than the original array. Right? It doesn't make sense to make a smaller array. Right? I have to copy all the elements from the old array into the new array. Right? Now I've made a new array, so I have to make my field, this.arr, I have to make that refer to the new array. Right? So I have to assign the new array to this arr, and then you go ahead and push the element onto the stack. Right? So in other words, I have to increase the capacity of the existing array and then add the element into the new array. Right? Now, how much more capacity should you add? Right? So if I want to push one more element onto the stack, should I just make the array one element bigger? Right? Should I make it 10 elements bigger, or should I make it some other number of elements bigger? Right? So it turns out what we're going to do is we're going to make the array 2 times bigger than the original array. Right? So how do you make a new array? Well, you just use new int. Right? How big is the new array? It's just the length of the old array times 2. Right? Now it turns out if you multiply the old capacity by some value bigger than 1, right, then you can guarantee the quote-unquote optimal complexity of this step. Right? If I just added a constant number of elements, it turns out this is going to make your push operation O(n)². Right? Proving that is beyond the scope of this course. Right? If you double the capacity or multiply it by 1.5 or something like that, you can guarantee that the push operation has worst case complexity O(n). I don't know where they're going to teach you that. They're either going to teach you that in the data structures course or in the algorithms course. Right? But it's not really appropriate to teach you here. Okay, so I'm going to double the capacity of the array, right, by making a new array. Now I want to copy all the elements from the current array into the new array. So what I can do is do that using just a loop. Right? So starting at index 0, right, copy the elements from this array into the new array. Right? So easy peasy. Right? Now make our field, this array, refer to the new array. Right? And now I can add the element to the end of the array. Sorry, not to the end. I can add the element to the end of the stack, or to the top of the stack, sorry. Right? So you could repeat this code up here, right? But I'm going to do something silly and just recursively call the method. Right? So I'm just going to recursively push the element onto the top of the stack. Right? When the method calls itself, the first thing it's going to do is it'll end up in this this part of the if statement here, right? And it'll add the element to the top of the stack that way. Right? All right. So the only tricky part in this class is this adding capacity to the array. Right? That's the only thing that's really hard here. Everything else is just some simple bookkeeping. All right? So it turns out that when you're working with arrays, this expanding or shrinking of an array turns out to be a very common operation. Right? It's so common that there's a method that does it for you. Right? So in the arrays utility class, there's a copy of method that will copy an existing array into a new array for you. Right? So instead of writing all of this, right, you can replace most of that with the following. Right? You can just write that. Right? So arrays copy of copies that array, or makes a new array by copying that array, and the new array has that capacity. Right? And it returns the new array with the copied elements in it. Right? So instead of writing the loop, instead of making the array manually yourself and then writing a loop to copy the elements, just use arrays copy of. Right? It does all the work for you. Once you know about copy of, this method becomes very simple to write. Right? It's just 3 lines here now. Okay, any questions about that, about using an array to store the elements of a stack? All right. Let's go back to the beginning of the lecture. Okay, so in one of your previous courses, you should have learned about recursive methods or recursive functions, right? So functions or methods that call themselves. The reason you don't want, in general, you want to avoid recursive methods because they can only solve, in most cases, they can only solve problems up to a certain size. Right? When you try to solve a problem of a bigger size, then what ends up happening, you end up with some funny out-of-memory error. Right? And so normally what happens, so in Java, you end up with a stack overflow error, which is actually trying to tell you that you've internally, the Java runtime is using a stack. Right? And so the reason this happens, I'm going to show you why this happens. Right? And so what I'm going to do is I'm going to use these pretty primitive memory diagrams that we've been drawing. And I'm going to draw a memory diagram of what happens when you run a recursive method. Right. Okay, so here's a method that you should never write. Right? It's called power of 10. So this calculates 10 to the power n. Right? Yeah. Right. So it calculates 10 to the power n, where n is greater than or equal to 0. Right. Now to do that, you would never do it this way, right? So you'd never do this using recursion. In the worst case, you would write a loop, right? But preferably, you would just call math.pal, right, and let it do it for you. But if someone asked you to do this recursively, you would end up writing something like the following, right? So if n is 0, you're done, right? Because 10 to the 0 is 1. So you just return 1, right? If n is greater than 0, then you return 10 times, right, the power of n minus 1, right? Because 10 times 10 to the n minus 1 is just 10 to the n, right? And so that's a really very, very simple recursive method, right? Okay, now what happens when you call this recursive method, right? So here's my main method, right? My value x is going to store the value of 10 to the 3, right? So what happens is this method gets called. Right? Now when a method gets called in Java, that method eats up space in memory somewhere. Right? So it takes up space in what's called the call stack. Right? So somewhere in memory, a version of power of 10 appears. Right? That parameter, or that argument 3, gets stored in the parameter n of the method. Right? So there's a parameter n here. Right? So that parameter n, you need somewhere in memory to store that. right? So that gets stored here on the call stack, right? And so that value of 3 gets passed to the method, right? That method computes 10 times the power of 10 times the power of 10, 2, right? So if you go back and look at the method, right, we're not in the first case because n is not 0, right? So we end up in the else part, and in the else part, it calls itself passing in 2. Right? So the result, which also takes up memory, right, on the call stack, right, the value of 10 times power of 10, 2 is stored in result, right? But that's another call to a method, right? So that method appears on the call stack, right? That 2 appears in the parameter n of this version of the method, right? Not this version of the method, right? Every time you call a method, a new version of that method appears, right? And the result, well, it stores the value 10 times power of 10, 1, right? But that's another method call. So that method appears on the call stack somewhere, right? That value of 1 is stored in the value n, the parameter n for that version of the method, right? And the result is 10 times power of 10, 0. Right? Now power of 10, 0, right? So that's another method call, right? That 0 gets stored here, right? Now this hits the base case of the recursive method, right? So the result is just 1, right? Which is at the very bottom there. It's cut off a bit, but it's at the very bottom, right? Right? So the method, that version of power of 10, right, ends up with a result. And that result gets passed back to the caller. So in other words, that 1 gets passed back up to here, right? And when it gets passed up to here, this version of the method disappears off the top of the call stack, right? So that gets a 1, and that version of the method disappears, right? 1 times 10 is 10. So this version of the method now has a result, which gets passed back up the call stack, right? So that 10 goes up there. And this version of the method is now done, so it disappears. Right? Now we have 100. That 100 gets passed back up the call stack. Right? This version of the method is done, so it disappears. Right? Now this method finally has a result, so that result gets passed back to the caller. Right? And now this one goes away. Right? And so if you reverse the sequence of operations, right, a version of the method gets pushed onto the top of a call stack, which calls another method, which gets, right, which calls another method, which calls another method, right? And so this sequence of operations is literally a stack, right? It's actually, it really is a stack. So it's a stack that's running, that your Java runtime manages, right? And you can see what happens if you start with a very large value of n, right? If this was like 1,000, I would have 1,000 copies of this method on the call stack, right? And the problem is the call stack on the call stack in most programming languages has a fixed size, right? Because the memory where the call stack is stored is a very fast version of memory, right? And so it's limited because you only have a limited amount of that memory on your CPU, right? And so your call stack has a finite size. If you have a recursive method that has a very large input, it ends up eating up more space on the call stack than there is available, right? And what ends up happening is your program ends up crashing. Okay, so if that sequence of method calls is just a bunch of stuff getting pushed onto a stack, right, then instead of using the call stack, I can just create a regular stack and push all the information I need onto that regular stack, right? And in that way, I can avoid writing a recursive method, right? Now, this is tricky to do in general. So in this case, it's easy. But in general, it's hard to know what information you need to put onto the stack. Okay, so in power of 10, what needs to be done when each recursive call returns? Right? So every time a recursive call returns, right, if you just go back and look at the source code, right, then what ends up happening is the value that gets returned by the recursive call gets multiplied by 10, right? Because it's computing 10 times 10 to the power n minus 1 each time, right? So you need to multiply the return value of the recursive call by 10. Right? So each recursive call that's not a base case is going to push a 10 onto a stack. Right? So what I'm going to do is I'm going to push all the 10s onto a stack. Right? So what happens to the value of n every time you make a recursive call? Well, it goes down by 1. Right? So make a stack. Right? Now I'm going to emulate the recursive calls. Right? So while n is greater than 0, right, I'm going to remember that I have to multiply the result by 10 each time. Right? So what I'm going to do is I'm going to push a 10 onto the top of the stack. Right? And then I'm going to decrease n by 1, right, to indicate that, hey, I've called the recursive method once. Right? And so what ends up here is you end up with n copies of 10 on a stack. Right? So a recursive call that reaches the base case results in a value of 1. Right? So in other words, when n gets 0, you end up with a 1. Right? So when n gets 0, my result is 1. Right? Now I'm going to unwind the call stack. Right? Just like the virtual machine unwinds the call stack. Right? So I start with a 1, and I'm now going to pop the stack until it's empty, each time multiplying by 10. Right? So pop the stack. That's going to give me a 10. Multiply that 10 by the current result. Right? So 1 times 10 times 10 times 10 times 10 n times. Right? And that gives you the result. Right? And so now you've converted your recursive version of the method to an iterative one. Right? There's a loop here. There's a loop here. Right? The stack is simply storing that 10 each time. Okay, so using a stack in the previous example, that's too complicated for actually solving that problem. Right? You would never write it that way. Right? But it illustrates what you would have to do if you have a recursive method that you want to turn into an iterative method. Right? That's a mistake. There is no other example here. All right. Anybody have any questions about using that, about the stacks and our implementation using an array? I don't really care about the recursive part, so I'm not going to ask you about that on the exam or anything like that. That's more for your knowledge moving forward, right? So when you hit your data structures course or your algorithms course, it might make more sense to you when they tell you how you take how to convert a recursive method into an iterative one. All right. If there's no questions, that's the end of this lecture. Assignment 5 will appear tonight. It's almost done. I just have to finish writing it up.